Good morning and welcome to today's webcast, Heinz Block, Lubrication and Failure Avoidance. I'm Stephanie Romano, editor of Hydrocarbon Processing, and I'll be your moderator today. Joining me today is one of the world's foremost experts on maintenance and reliability, Heinz Block. Heinz Block is an editor for Hydrocarbon Processing for over 10 years and has built a dedicated following worldwide in his area of responsibility. He holds 6 U.S. patents, has authored over 460 technical papers, and 17 books on machinery. He was an Exxon chemical machinery specialist and held positions worldwide before retiring after 24 years of service with Exxon. Today we'll cover lubrication and failure avoidance. We would like to thank today's sponsors for making this webinar possible. First of all, Royal Purple, who is recognized as one of the leaders in lubrication technology. Royal Purple produces a wide range of high-performance lubricants for nearly every industrial application. They have advanced additive technologies that enable it to produce and to outperform leading synthetic and conventional lubricants. Today, Royal Purple continues to commit significant resources into research and quality assurance to ensure that it continues to raise the standard of excellence in lubrication. We also like to thank T.F. Huggins Lubrications. Their products designs and fabricates, installs, and services a wide range of custom lubrication systems to meet your specific needs for any compressor, engine, pump, or machine application in any working condition. For more than 60 years, they have helped maintenance professionals in a variety of industries achieve optimum lubrication for machines such as compressors, fans, and pumps. Their lubrication systems experts perform on-site audits, analyze your existing equipment and operation, and will prepare a detailed report with recommendations for improvement, all at no cost. You'll find all the answers you need at T.F. Huggins. Please visit them at their website, www.tfhuggins.com. Also, ABB Level Measurement. They are a leading global manufacturer of state-of-the-art instrumentation for bulk solids and liquid level detection. Now with the power of K-Tech technology, they have over 425,000 installations worldwide in such applications such as oil and gas and chemical processing, pulp and paper, mining, construction, and the food and beverage industries. ABB Level Measurement operates at manufacturing and service locations around the globe. You can find more information at www.abb.com. During this presentation, at the end of this presentation, we will have a short question and answer session. You can participate in the Q&A by asking questions at any time during the presentation. Just type your question into the Ask a Question text area in the bottom corner of your screen, then click the Submit button. You may enlarge the slide window at any time by clicking on the Enlarge Slide button located below the presentation window. The slides will automatically advance throughout the event. If you experience problems with the program, please press the F5 button on your keyboard or close your window and relaunch the presentation using the other media player. You can also visit our the webcast help guide by clicking on the Help button before the slide window begins. So let's get the webinar started, and we'll turn the presentation over to Heinz. Heinz?
Yes, good morning. Let me then move to the first slide and start out by telling our audience that we have in lubrication for machinery, again, 7 cause categories which cover all problems. The interesting part here is that as you look at the sequence of 7 possibilities, faulty design, material defects, and so forth, you should not look for an 8th one. All flaws, all difficulties, all deviations that are related to lubrication of equipment can be found in one of these 7. As I go on to the next slide, I might highlight the machines that we're dealing with and also the major topics that we can cover in a 1-hour presentation. The machines are recip compressors, turbo machines, gear speed reducers, we will briefly talk about them, and certainly process pumps. There are issues with lubrication in each one of these. And so as we go to the next slide, you can see that lubrication selection is one of the areas that is very frequently overlooked. Viscosity is the most important property of a lubricant. And it is also the most important single physical property of a lubricant, the viscosity. The notion, as you look at point 2 up there, the notion that one oil fits all is simply not true, and we shouldn't lose any time in debating it. We are dealing with petrochemical companies. We are dealing with process companies that are listening in on this presentation. And again, you need some special lubricants in order to be an advanced manufacturer of whatever it is that you are doing. Single oil does not fit all of your needs. Look down a little bit more towards the middle of this particular slide. It deals with friction, and it says oil drag or viscous drag may cause oil rings to malfunction. This is a topic that we'll deal with in a few minutes. And also, if you have this frictional drag of oil rings, you will increase the power requirements to the particular piece of machinery that we're dealing with. Move, please, to the next slide. And this is where I'm giving an overview, a brief overview, obviously, of the types and functions of additives. And they convey a message. And the message is, of course, that lubricant selection involves competent formulators, and inexpensive lubricants are rarely, if ever, of great service to you. And instead of trying to be too detailed in my presentation, in my overview of lubricant selection, what you should take away from my comment is simply this: make the better formulators of synthetic lubricants, make them your tutors. Be on their side, let them advise you, interrogate them, learn from them, and upgrade your lube selection. Do not do what I have occasionally seen in industry, and that is purchase your lubricant from the lowest bidder without paying any attention to the importance of additives. Good additives cost money. You have to pay for it, but you get a tremendous payback if you procure your lubricants from someone who can properly advise you. On our next slide is simply an overview of the performance benefits that you will be getting from synthetic lubricants. High oxidation stability is one of the performance factors that sets apart good synthetic lubricants from mineral oils. Below that, still in the same column, you see the word excellent lubricity. And on the right, there is a listing of what excellent lubricity really means. It means, for instance, reduced equipment wear from this improved lubricant film. It means longer equipment life, less downtime, and so forth. And again, I am simply, from experience, advising you to communicate with the most competent formulators of synthetic lubricants. They will tell you the truth. They will have to be paid for it. They are not going to be your lowest bidder on the basis of per gallon lubricant cost, but they are going to be, in the end, by far your best provider in terms of the overall runtime of your equipment. On our next slide, we say the same thing, but in a different format. You can see how mineral oils have a continuous service capability in a temperature range from probably 0 degrees Fahrenheit, which is about 18, 20 degrees negative Celsius, to a plus 200 degree Fahrenheit temperature. And on the right, you can see how in intermittent service, for instance, the synthetic oil will go from minus 50 degrees to plus 400 degrees Fahrenheit, or even higher for short-term time periods. So there is a very noticeable extension of the operability range with properly formulated synthetics. On our next slide is probably the most important summary I can convey to our audience with regard to where it is without question cost justified to use synthetic lubricants in 6 principal areas. Automotive lubricants are one of them. Of course, we're not dealing with this. We're dealing here with an industrial audience, but we know from our personal automobiles that we own that in this day and age, we would undoubtedly purchase only synthetic lubricants. They have low friction. They give you extended drain intervals. The same properties, low friction, extended drain intervals, are true for your industrial equipment. You go to point 2, and it says rolling element bearings that show vibration activity due to microcracks. They will actually undergo a reduction in vibration severity in the majority of cases if you convert to a synthetic lubricant. The third item is gearboxes, especially the cooling tower fan gearboxes. If you want to extend the life of these gearboxes, you cannot do that with mineral oils. With mineral oils, you have more frequent change-out intervals for the lubricant. You have high costs for shutting down fan gear during the time when you replenish the oil. On the other hand, with a properly selected gearbox to begin with, and with using synthetic lubricants, there are many gearboxes that have a life of 20 years and longer before anybody ever opens them up, before anybody ever looks at the teeth. Item 4 is closed-loop oil mist lubrication. Big savings there if you put an entire refinery on closed-loop, centralized oil mist lubrication. It's a subject unto itself, and we have covered that in one of the previous webinars. The fifth one we will briefly go into a detail in just about 2 minutes, deals with reciprocating compressor cylinders. This is where synthetics extend the life of the valves and the piston rings or rider bands, and it is not appropriate to assume that you will become a best-of-class company if you continue to use mineral oils for reciprocating compressor cylinder lubrication. And the last one is item 6. In many oil-flooded screw compressors, a properly formulated synthetic is vastly superior to a mineral oil. If we go to the next slide and briefly ask ourselves the question, what is poor lubrication? Well, remember how roughly 15 minutes ago we talked about the 7 root causes of machinery failures. One of these was maintenance related. And if during maintenance you make mistakes in the setting of the level of a lubricant, or if you think you save money by purchasing the least expensive constant level lubricator, well, then you have a high risk of going into poor lubrication. Corrosives enter into the lubricant. The lubricant oxidizes prematurely. It may have the wrong viscosity, or you may simply get dirt into it. And all of these are troublesome to your rotating machinery. I'd like to be a bit more specific and show you this particular slide. This is called a constant level lubricator. A constant level lubricator bulb is shown in the right foreground, and you can see the oil in there. And the oil is actually going to the very top of this lubricator bowl. This is a lubricator that cannot possibly function properly. It cannot properly function because the lube oil level in that bowl is too high. There needs to be a certain amount of air near the top of that lubricator bowl, and it has to do with simple hydraulics. The air near the top of that lubricator bowl is at less than atmospheric pressure. Then, of course, there is a certain pressure exerted by the amount of lubricating oil that you have in that bowl. Hopefully, it should be only half full. And then those two pressures together should be identical to atmospheric pressure. But if, as shown in this slide, the lube oil level is too high, you cannot properly lubricate this pump. And here is another small item of interest. If you take a careful look, there is a lubricator bowl in the front left of the picture, and there is also a lubricator bowl in the rear right of this picture. Both of these cannot be correct because these lubricator bowls are sensitive to the direction of rotation of the shaft. You see the shaft, of course, in the lower left corner, And if this shaft is rotating counterclockwise, in that instance, the front lubricator is correctly installed on the left of the bearing housing. However, the rear lubricator is then installed on the wrong side of this pump. And what we're simply pointing out is, if any in the audience aren't familiar with that, we do not have the time to go through this whole thing because we cannot spend enough time on the rest of the slides if we do that, but you are strongly advised, or it's recommended for you, to pick up appropriate texts and books which explain in detail that the lubricator must be mounted on the correct side. If it's not mounted on the correct side, you will have high risk of failure of the equipment. Our next slide now deals with compressor lubrication, and of course, as you know, there are recip compressors, there are also centrifugal compressors. And so what I want to show you to begin with is a plain schematic. And at the top of this schematic, we're saying that in all machines, the oil type and the application details have to be just right. Just right for what? Well, for long life. And the example schematic here is for a recip compressor. And it shows a pre-lubricating pump, which is near the middle of our schematic. And it shows a frame-driven pump, which is shown at the bottom of the schematic. And it shows that there is, to the right of the frame, please identify the frame first. Frame is on the left of our picture. And slightly to the right of that frame, there is a vertical line which says, to compressor cylinder lube. Well, if you go and use that line and connect that to your compressor cylinder lubricating system, then that implies that you're actually using the frame oil. The same oil that you use for the frame is what you seem to be using here for cylinder lubrication. And if you remember 10 minutes ago, we said that cylinder lubrication for reciprocating compressors should be done with synthetic lubricants. So there is a basic oversight in here. It is implied in this schematic that the frame lubricant is the same as the cylinder lubricant. And you cannot be a best-of-class company if you are using a mineral oil for lubrication of your compressor cylinder. We go to the next slide, and this one refers to a centrifugal compressor. And the point that we are trying to make on this slide is that optimizing the lube and seal oil system in a centrifugal compressor requires that you carefully observe the schematics that are given to you in the API specifications. In the API specifications, a schematic very often will show you two filters and will, of course, show you two coolers. It will also show you in the lower right-hand corner of this illustration of this schematic a lube oil reservoir. What it doesn't show you is that in a real high class or low risk of failure type lube oil reservoir, you would not want to use electric heaters. You would probably want to use steam coils. And you would probably want to heat up a fluid that would be located below the slanted or sloped bottom of this reservoir that you presently see in the lower right-hand corner. Again, this is an interesting topic which has been discussed, of course, in many of the books that Ms. Romanoff has mentioned at the beginning of our conference here. I will go to the next slide and will show you a particular item that will be used by companies that are best of class. They would use not the traditional hydraulic accumulator that you see to the left of this image. They would instead be using a diaphragm type accumulator, which you see to the right of the image. The conventional low-cost bladder type accumulator that you see on the left when that bladder stretches and contracts and stretches and contracts, it will have some frictional contact with the inside of the wall of the accumulator vessel. And because of that frictional contact, that particular bladder may break at one time or another, perhaps after 2 years of operation, and nobody will realize that it has broken. Whereas if you do what best-of-class companies are doing, procure a diaphragm-type accumulator, the one that you see on the right of this image, well, then you have a diaphragm which moves up and down and which has a rod that is mounted in the middle of that diaphragm. And then at the top of this spherical accumulator, like a big sphere, and the top of it, you have a transparent dome. And the operator can see whether the diaphragm is near the top or near the bottom, or where you really expect it, near the middle of the plastic dome. And again, this is explained in books, and it goes beyond what the API specification requires, but it is simply an ingredient of what people do who call themselves best of class. Here you can actually see one of these diaphragm-type accumulators. You can actually see that there is a gas bottle to the next of it. It's a nitrogen bottle. And the nitrogen bottle is, of course, used to refill the diaphragm-type accumulator if occasionally the operator sees that the positioning rod, which is like a plastic dome on the accumulator itself, if the positioning rod is no longer at the right location, perhaps after 2 years of operation, some of the nitrogen has escaped, and then he refills it from that. But the point is that the operator will use his eyes, and he will visually observe whether this particular diaphragm-type accumulator is properly filled. The next one has to do with lubricant preservation or cleanliness, and so we're dealing with lube preservation in general on rotating equipment. And very frequently you see, of course, especially on small equipment, that someone is utilizing a bullseye sight glass. You see this bullseye sight glass right in the middle of our image. You can also see in the lower right-hand corner of this picture that we are occasionally finding sight bowls which people are selecting for the purpose of observing whether water has gotten into the equipment. But by far the best way to have proper maintenance and proper reliability endeavors in equipment that you have in your plants is to prevent the issues from coming up in the first place. You prevent the issues by, as it says in the upper left-hand corner of this image, by finding oil contamination sources and entry points. So if an oil contamination point or an entry point is near the middle of this bearing housing, then maybe you have a loose fill plug, or you have a vent, or you have, I said, people who don't pay attention what they are doing with a vent of this type. Many pieces of machinery, I might again say, as I said in a previous webinar, many pieces of machinery have no vent. They are sealed. Just think of the millions upon millions of refrigerators that we have in homes, or refrigeration sets that we have in an automobile as part of the air conditioning unit. All of these are totally sealed. There are no vents. The very notion that you must have vents is perhaps somewhat antiquated, to say the least. I'm simply saying to you that modern equipment is designed so that there are no entry points for dirt and contaminants. And as we go to the next slide, we see a picture slightly amplified. It's actually a picture that shows bearing isolators on the extreme right and on the extreme left near the bearing housings of this small pump. And so near the bearing housings of these pumps, you would usually have, of course, in old pumps, a lip seal. In new seals, a rotating labyrinth seal. And the next picture shows it slightly better in schematic form. It shows you a small steam turbine. And in that steam turbine, again, we have to the right and to the left a point where dirt could enter into the bearings. And in order to prevent dirt from entering into the bearings in this particular picture, the equipment owner has specified or has retrofitted some bearing isolator seals. The bearing isolator seal is shown in the lower right-hand corner, as we just mentioned, and it consists of a rotating component and a non-rotating component. And whenever you contemplate the procurement or the use of bearing isolator seals, anything that prevents dirt from getting into the equipment, you should really take a very careful look at the cross-sectional view of the equipment. If it is a cross-sectional view, as you see here in the upper left-hand corner, then notice how I gave an explanation. The explanation is always examine how different bearing protector styles really work. When a dynamic O-ring contacts a sharp edge, as it does in the protector seal that you see in the upper left, then you risk serious damage to the O-ring. If, on the other hand, there is a well-contoured surface that you see in the lowermost segment of that particular slide, that means you have low pressure and very low failure risk. You can also note the difference between the upper left and the upper right. Both of these use a single O-ring to clamp the rotating part to the shaft, whereas the part that you have in the lower portion of that slide, the rotating part, uses two O-rings to clamp it to the shaft. So you ask yourself which one is the greater risk. You research that. There are plenty of books, and there is lots of information available that explains the difference in even greater detail than what I have done now. There's also, as we go to the next slide, a very frequent tie-in between lubricant application and repeat failures in rotating equipment. So what do we mean by that there is a frequent tie-in? Well, the tie-in has to do with the fact that all of the machines that we are dealing with have, of course, a shaft which protrudes through a casing in one way or another. But also there is lubricant application that differs from machine to machine. And the lubricant application that some of you that are online are frequently seeing is somewhat similar to what we attempt to illustrate here on this slide. This is a vastly overlooked issue. It's an issue that has to do with the fact that many of your bearings are angular contact bearings. If you take a close look on this angular contact bearing, there are surfaces between the rolling elements and the raceways that are at an angle. And so the load line is going through this bearing ball at an angle of approximately 40 degrees from left to right. Now, if one attempts to put lube oil into a region to the left of this bearing, then the lube oil is being fought by the fan effect of the ball separator of this angular contact bearing. Take a close look at this bearing again. It's an angular contact bearing. The ridges, or we might say the raceways that are to the left of the bearing ball and the raceways that are to the right of the bearing ball are of unequal height. Therefore, the ball separator or cage that separates the rolling elements is at a slight angle. And because it's at a slight angle, it causes windage, just like a fan or even an impeller is causing flow from one side to the other. That's what happens with this particular ball separator or cage. And the windage flow, the airflow, is from right to left, whereas in many cases you're attempting to have oil flow from left to right, and the two fight each other, and as a result, you don't get adequate lubrication. And that is, again, explained in many pictures, and it's also explained in many books. And I'm summarizing some of that by, again, showing you a pump picture. Shows the inboard bearing, which is sometimes called the radial bearing. Shows the outboard bearing, which is usually called the thrust bearing. It shows the pump suction and the pump discharge. And you can visualize from a picture like this that you must protect the lube oil by using bearing protector seals, which was the topic 2 minutes ago. And you must protect the lube oil by making sure, you must protect the bearing, by making sure that there is not windage that fights the application of the lubricant. Now, if you're asking me, well, why is a manufacturer of pumps selling me this? Well, the manufacturer of pumps may not realize what I have just explained to you. The manufacturer of the pump may say, well, we want you to change the oil once every 3 months. And if you do that, maybe you have not yet damaged the bearings. But in a forward-looking plant, in a best-of-class plant, one changes the oil in a typical bearing housing of a pump every 2 years. One changes it every 2 years because one has protected the bearing against dirt and against water intrusion and has made sure that the oil application is correct. If you took a look at the top of a bearing housing by simply removing the vent or the filler cap, you will often see that there is an oil ring and the oil ring is bouncing around. And what I would like to confirm here is that because oil rings bounce around, you can just imagine what happens when they touch the inside of one of the components of the bearing housing. In the left picture, it says the ring was immersed far too much. This caused the bearing to burn up. You can see in this image that there is sludge, oil sludge, which is near the bottom of the image. And on the right side, it says the ring was immersed 1/8 of an inch above the inside of the ring, and this is correct. So in this case, the right side, you don't have as much discoloration. So there is great difference when you use oil rings between proper application and improper application. Proper application of an oil ring will primarily have to do with using the right viscosity oil, the right amount of immersion, and which also means that you have to keep away from that ring any kind of disturbing member. You cannot allow the ring to touch the inside of a bearing housing. If you allow it to touch the inside of a bearing housing, here is what will happen. You can see that there are two images. I'm going to describe only the image that has the two rings standing vertically. The ring on the left is a good new ring, or almost new ring. It has a chamfer on each edge. It has very little discoloration on its inside. If you would measure the ring on the left, it would be substantially wider than the ring on the right. The ring on the right has abraded. Flakes of that ring material have contaminated the oil and have gotten into the bearing and have prematurely ruined the bearing. So you need to understand that rings, unless they are made by a manufacturer who properly heat treats these rings and stress relief anneals these rings, unless they're made by a manufacturer who takes proper care and will have to ask a certain amount of money for it, cannot possibly be the lowest cost manufacturer. Unless you use that kind of ring, you will have great risk of premature failure. Of course, also, as we said 2 minutes ago, if you overfill the oil, then the ring will not function correctly. So these are the reasons why best-of-class companies try to stay away from oil rings. Here you have an image which was contributed by the Trico company. They make these constant level lubricators, but it shows you what happens when you have a high amount of wind blowing across an opening of this type. You get what is called a Venturi effect. And when you have a Venturi effect with an open system, and this is an open system lubricator, you are changing the level of the lube oil in that bearing housing, and your operators and maintenance people don't even know what is happening. And there's another image that goes a tiny bit further from the same company, Trico, And they also offer you a closed lubricator. A closed lubricator makes sure that the windage effects that we have just seen are less pronounced. And this would be the only lubricator that you would find in a true best-of-class company. We look at the next slide, and we see a close-up of the closed system constant level lubricator. We can see that there is a balance line which goes from the center of the bearing housing to a place somewhere mid-span in this particular lubricator. Notice also that the lubricator is only half filled because 20 minutes ago I clearly explained from another image that if you have a lube oil level going all the way up, you cannot possibly properly lubricate the bearing. It is not possible. It goes against the laws of hydraulics. So anyway, if you need additional explanation, then there is literature available from one of the many papers that I have written over the years, from one of the many books that are available, and the last one we'll see in a few minutes. But in any event, lube oil levels are simply underrated. They are not paid attention to sufficiently. The types of sight glasses that are used are frequently inadequate. A better sight glass, without question, would look different from the one that I'm showing you on this particular slide. This is why I said early on, work with good vendors, people who know what it is that you need to be a high reliability installation. And these then are sight glasses that are extended, they protrude somewhat, and these are better than the less expensive sight glass that I had shown you on the previous slide. This is the only one that I would use in my plant if I must use sight glasses in the first place. So now our presentation is briefly going away from lube application, and we're seeing something that has to do with elementary cooling. If you are working in a plant that allows the use of open streams of water to cool what someone has perhaps claimed is a hot bearing, then you set yourself up for real difficulties. If you use this kind of external cooling, you're causing the outer surface of the bearing housing to shrink, because after all, when you cool a hot surface, it will shrink. So by cooling the outer surface, which is all you're doing here, you're shrinking actually the clearance between the bearing bore and the shaft. And the bearing is now more likely to fail than if you had left it alone and if you had not applied the cooling. Again, this is explained in texts of the type that you will see in just 2 minutes. There are also issues that need to be explained that have to do with the use of inexpensive couplings. The coupling that you see behind this particular guard, that is a coupling that is made out of an elastomer. And this elastomeric coupling is, number one, difficult to balance, and number two, when you operate it at high speeds, it has a tendency to fail rather prematurely. So component upgrading is something that is practiced by industry. Now, why is this part of our presentation here on lubrication? Well, the presentation on lubrication has to do with the fact that this particular coupling cannot be properly balanced. As a result, you have greater vibration in this electric motor or in the adjacent bearings of the pump. And if you have greater vibration, then you also have greater difficulty to keep the lube oil cool. It will somehow heat up. So you have an influence, a secondary influence that comes from the coupling in this case. Now, all of these problems you could, of course, avoid if you had plant-wide closed oil mist lubrication systems. This is just an image of a large-scale closed oil mist lubrication system, oil mist distribution system, how it's configured overall. Again, there are books that give you highlights of that, including a book that you will see in just a minute. And it is very important that in this day and age, we do not use open oil mist systems. We should instead use closed systems. In the left-hand corner, the extreme left of this image, you see a collecting vessel. All the excess oil mist that comes off these pumps and off these electric motors is collected in this collecting vessel. You might even be able to reuse the lubricant after sending it through a filter. So these are very, very appropriate system for plants that wish to be highly reliable. I had mentioned in the very beginning of our presentation this morning that without question, a cooling tower fan gearbox requires a synthetic lubricant if you want to make this gearbox live as long as it is living in one of your competitors' plants. And so here we show one of these boxes, these vertical fan boxes, and as a result of having an input shaft here, an output shaft here, and the application of synthetic lubricants to cover some of the gear, you have now at the top of it an empty space. Well, that empty space should actually be filled with oil mist, and the oil mist is generated by one of these closed generators that you've seen on the preceding slide. And if you very carefully look, there is an insert picture, and the insert picture has this blue frame around it, and at the bottom of this cooling tower, there is an oil mist system. Personally, of course, I'm familiar with oil mist systems that have been installed on dozens of cooling towers 30 and 40 years ago and have really been in service for all of those years with very, very little maintenance and have served outstandingly. And they are part of the secret of why some plants are more reliable than others. So now our presentation, since we wanted to leave 15 minutes for questions and answers, our presentation covered only the highlights of certain machines. You recall we talked briefly about recip compressor lubrication, turbo machinery, steam turbines, where we highlighted in particular the importance of steering clear of some of the oil rings that warp. And we also talked on steam turbines about bearing protector seals. On speed reducers and speed increasers, we talked about the absolute need to go with synthetic lubricants and steer clear of mineral oils. And finally, we dealt briefly with process pumps, where, among other things, I have shown you how a closed oil mist system is ideally suited to provide lubrication to an entire plant with its process pumps either running or not running, with its drivers, the electric motors, either running or not running. You always are on that closed loop system. Our final slide then is this one. Many books and articles are relating these facts to you. This is a book which is called Pump Wisdom, and I have tried to put into this book the things that are most frequently overlooked. What's overlooked on pumps is what causes repeat failures. Now think about what I just said. What causes repeat failures are things that are being overlooked. Why do you have repeat failures? Because you have not uncovered the root cause reason of why a pump failed. It may fail because you have perhaps oil rings that are not quite properly installed with true shaft horizontality. They run downhill. They strike the inside of a bearing housing. Maybe your immersion depth is not correct. Maybe you're using the wrong viscosity of the lubricant. Maybe the concentricity of the oil ring is incorrect. About 2 years ago in South Texas, I saw an oil ring that was 30 times greater out of tolerance than what the maximum allowable tolerance should have been. 30 times worse than what it was supposed to be. Then the oil ring bore finish finally should be about 32 RMS, and that sort of summarizes what I wanted to say on books, on articles, on vendor contacts, on making the vendor your mentor and your technology resource. And now we have time for questions. We have just about 15 minutes, and I would invite you to let me have the questions, and I will try to answer them. and also some of the questions can be answered by email.
Well, Heinz, that was thoroughly enlightening. I want to thank the audience this morning. They have been sending questions throughout the presentation. You still have time. Please do submit, but we have some great questions to get started with. And since we're just leaving the subject of oil mist systems, and I do want to remind our audience that that is the subject in seven recent articles in hydrocarbon processing talking about oil mist systems. Our listener comes in with the question, are oil mist systems highly expensive? He has worked on projects, and there's never been a philosophy on them, possibly due to ignorance, or maybe to save capital expenditures. Can you talk a little bit more about the cost for installing such a system?
The cost of a system is typically such that the payback is 2.5 years. And the payback is somewhat more rapid when you are operating in a humid climate where it is so important to keep humidity out of the bearing housing. It's also somewhat higher. Payback is more rapid when you are operating in a desert climate where you have occasional blowing sand. And the long and the short of it is that a capital project in a company such as ExxonMobil will always be based on not the cheapest equipment, but on the most reliable equipment. So the person who is asking the question is probably well advised to see to it, as I did 40 years ago, that the cost estimating manual that we use for projects reflects not the cheapest machine, but the best machine. And that's where it points inevitably to the use of plant-wide oil mist systems for the preservation, for the protection of bearings and of pumps and of rotating equipment that is equipped with rolling element bearings. So the long and the short of it is, if we look at life cycle cost, oil mist systems make economic sense.
Okay. Continuing at that, the oil mist lubrication subject, another listener has called in or written in. You mentioned closed loop systems. What is the benefit to a closed system over a once through system? Can you comment on that one?
The primary benefit is that if we're using closed systems, then we can truly say that we are conscious of the environment. Because if you're using an open system, then any of the stray mist, the mist that escapes, is getting into the atmosphere. Now, we can't have it both ways. We cannot be environmentally conscious, and at the same time, we always pay only the absolute minimum price. The two don't go hand in hand. The automobile that we are driving certainly has an anti-pollution device of one kind or another, catalytic converter and so forth. Now, to me, it's best technology that we should have. We live at a time when, for obvious reasons that we don't have time to go into, we should optimize on things that are giving us best long-term effectiveness and are best for breathing in clean air. And the answer to that is a closed system, and it's not an open system. I could get a cheaper car if I would not have my catalytic converter, but I'm a reasonable and sensible individual, and I don't want my children or grandchildren to breathe in dirty air. So therefore, I make sure that I have my catalytic converter on my vehicle. And it's the same thing, the same ethical view that should be used by industry.
Going back to the oil mist systems, we have another one. I know that you probably covered this, but help us out. The listener has written in, okay, what do you recommend as the best type of lube oil for oil mist systems? And I think you maybe just a refresher on the pros and cons of various synthetic lubrication systems.
There's one very important thing that needs to be pointed out. We very often have bearing housings, like, for instance, on small steam turbines, 200 horsepower steam turbines. We have bearing housings where the best oil is really supposed to be an ISO grade 32 for the oil rings. Because if you use an oil that's thicker than ISO 32 and you have oil rings, the oil is not properly fed into the bearings. However, the bearings, which are rolling element bearings in many cases, those bearings benefit far more from an ISO grade 68 oil. We're talking mineral oils now. So there's a conflict. The bearing application method wants ISO grade 32. The bearing itself wants to have ISO grade 68, and you can read that up on SKF and other bearing manufacturers. You can read up on it in books that I have published over the years. So there's a conflict between what the application method wants and what the bearing wants. If, on the other hand, you go with oil mist, or you go with a synthetic oil which has the strength and the capability in terms of protecting a bearing that is always above that of a mineral oil, then you can go with an ISO grade 32 synthetic, which will have the flowability that allows you to use the oil ring, but which has the strength and protective properties that you get from a mineral oil 68. So the answer to the question is synthetic 32. I don't want to call it an all-purpose oil, but if you want to really benefit both sides and you're not ready to replace the oil rings with something better, then stick with a synthetic 32. You cannot use a mineral 32. You can also not use a mineral 68 because it's too thick for oil rings. Next question, please.
Okay. I think you answered well, and you've also answered some of the negatives for some of these. Here's something that has to do with some information someone received from their vendor. When selecting oils for oil mist system, is there the truth that some manufacture synthetic mist oils reclassify is what they've used here, more efficiently than others, causing less spray mist? Have you run into that?
Let me put it this way. A competent manufacturer of oil mist systems, an experienced user of oil mist systems, will have no problem lubricating any rolling element bearing with oil mist. Someone who is not on top of the list in terms of competence may use the wrong reclassifier, or may adhere to the belief that one reclassifier fits all. I want to standardize on one reclassifier. That is not possible for those of us who want to be best in class. We realize that we need to have different reclassifiers for different bearings. In some cases, they need to be positioned differently. That's all explained in books, and I cannot really explain it in just 2 minutes here. But there have been articles in books, especially now this Pump Wisdom book, which explain this. And it's not that I'm interested in the listener buying the book so that I get 78 cents worth of royalty into my pocket. The interest is only for those who are really interested in reading this, in understanding this. The literature is out there, and you must read it, or else it's difficult to understand. Please don't guess at it. You're not going to do your company, your employer, any favor by guessing at these things. Next slide, please, or next question.
Yes, no problem, sir, no problem. Our listener has sent in, what kind of a purifier do you recommend for installing lubrication systems on a centrifugal compressor driven by steam turbines?
Well, there are either the thermojet type sparging units. They are units that are operating on the basis of sending in relatively dry air, and that relatively dry air is binding the moisture, and then the moisture is exhausted from that unit. There are also some units that are operating on the basis of a vacuum, so they are called vacuum dehydrators, and those are the ones that I'm most familiar with. I would look at some of the ones that are also advertised in journals and in some magazines, trade journals primarily, and would ask myself, can I contact that vendor? What is the experience that this vendor has? And then I have to compare them on a case-by-case basis. We have, at Hydrocarbon Processing, invited some of the manufacturers of different types of purifying units to write articles, to send articles. Some of them have not done it. So why they haven't done it, I don't understand. I don't know. Maybe they haven't had the time. Maybe they realize that we have a critical eye, and we sometimes call out certain inadequacies that we find in some of these systems. So in general, I would say systems that you can purchase from the Lube Systems Company in Houston have proven quite adequate. They're used by General Electric and are used by the U.S. Navy. And then there are some other units that are called vacuum dehydrators, and they have also been used at Exxon plants 40 years ago, 30 years ago, and I would look at them and make sure that they're up to date.
Okay, we have so many questions here. It's hard to, we're running out of time, so we're trying to pick our better things. Forgive me here. Here's one that goes back to the forgive me here. Oh, this is a different one. We hadn't touched this. We've been talking about heat, but a listener has written in, what special things must be considered when you're looking at a cryogenic lubrication system?
Mm-hmm. Cryogenic is, of course, extreme low temperature. We're dealing with temperatures where, for instance, in an air separation plant, one produces liquid nitrogen, which is ultimately really coming from the environment, from the air. So the lubrication system for a unit of that type, sometimes there's a preheater involved, and at other times one is simply using extremely low pour point synthetic lubricants. In all cases, you will use low pour point synthetic lubricants, but we need to know at what approximate temperature the bearings are operating. We even want to know, as reliability engineers, whether one needs to have lubricated bearings or whether one should go to air bearings or to magnetic bearings. See, a sophisticated machinery engineer will ask those questions also. In other words, instead of just asking what kind of oil do you use on a machine, which still uses somewhat outdated bearing systems, I would like to go a step ahead of it and would ask myself, does it need that kind of bearing system in the first place, or should it be upgraded to a bearing system that doesn't require oils?
Okay, we got a little bit more time here. This is another interesting one. We're talking about best-of-class performers. The listener says, why are electric heaters not of best-of-class? They are often spec'd by vendors in new equipment. If the vendor thinks it's a good idea, why is that not part of best-of-class performance?
An excellent question, and let me answer it this way. The problem is that the vendor is using these electric heaters, and they have a certain skin area. Let me just totally arbitrarily say to you, they give you a certain heater that has 100 square inches of outer skin. If you now put too much heat into that particular heater, because the vendor tried to save money by only giving you a single heater, and it has a skin of 100 square inches, and you're putting into it 10 kilowatt of power, then you are overheating the skin, and you're also overheating the oil. All the oil that comes in contact with this electric heater is going to overheat and will cause carbon formation. So now if the vendor gives you too many of these heaters, very many of these heaters, so that his watt density, the amount of kilowatt per square inch of surface, is very low, well, then he has to use so many heaters that you might as well have used steam heat. And so that's the issue. And unless you show me a vendor who is limiting the skin temperature, and which therefore takes a fairly long time to heat up a certain volume of oil, that's, of course, the crux, you see? And that's where reliability engineers' knowledge comes in. the next question, please.
Okay, I believe this is going to be our last question of the day, and I want to thank all the listeners today. We've had way too many questions, but Heinz will be looking into these questions later on this morning, or later on. I take that back to give you answers. Our last question is a question, and it's probably a detection one. The rise of temperature in a bearing, is it always due to lack of lubrication or something else?
Well, maybe there is enough lubricant going to it, but what is happening is that maybe the bearing surfaces have been scratched by dirt going through it, or maybe somebody has allowed the machine to vibrate at excessive amounts of vibration amplitude, in which case the oil gets squeezed out and you have shaft surface to bearing bore contact. So it is an issue that has to be, again, looked at carefully on an item-by-item basis. One looks at the temperature data before the incident and looks at the temperature after the incident, makes a decision based on measurements whether the clearance between the shaft and the bearing has been correct. And all of these are factors that then influence the decision as to where the root cause of the problem is.
Okay, and that is our last question for this morning's webinar. Again, we would like to thank our sponsors, Royal Purple, T.F. Huggins Lubrication, and ABB Level Measurement for their support that we were able to put on this webinar this morning. The webinar will be available on Hydrocarbon Processing's website within the next 24 to 48 hours, so you can rehear the presentation one more time. We thank you for the listeners, and if you have any questions, as always, please make Hydrocarbon Processing your first and last stop for answers on maintenance and reliability. This concludes our webinar on maintenance and lubrication and failure avoidances. Thank you all.